Hello dear, it's been exciting once more coming your homes, your various homes with making physics easier with say idea. Okay, today we are going to look at the helical spring or the loaded spring, and we are saying that the motion of a loaded spring is an example of oscillatory motion, which is also an example of simple harmonic motion. So today we are going to investigate what makes the motion of the helical spring oscillatory by nature. And so we are going to look at what makes the loaded spring or the helical spring oscillatory motion by nature and then simple harmonic motion by nature. Before we look at those key concepts, let us look at what makes a particular motion simple harmonic. We know oscillatory motion is the repeated to and fro motion of a body about a fixed or main point. The repeated to and fro or back and forth or up and down motion of a body about a fixed point is oscillatory motion. Then simple harmonic motion is the same, the repeated to and fro motion of a body about a fixed point whose acceleration is always directly proportional to the displacement, and the same acceleration is always directed to the main point or the rest position. Okay, so we are going to look at these key attributes of simple harmonic motion, which are, we are saying that the acceleration of the body, the acceleration is always directly proportional to the displacement. So A, which is the acceleration, A is directly proportional to the displacement. And then, so it means A is directly proportional to Y. And then the acceleration A is always directed towards the main point or the rest position. So what it's also, okay, so A is directly proportional to the displacement, and E is, the acceleration is always directed towards the main point. So when we put the two key attributes together, we have A directly proportional minus of the displacement. These are the key attributes of the body, attributes of a body in simple harmonic motion. So we are going to look at the helical spring. We are going to look at the helical spring and see, or the loaded spring, to see if it has these listed attributes. But what is a helical spring or loaded spring? This arrangement, okay, this arrangement is what we are calling as a loaded spring. Okay, there is a spring. The spring is weighted or loaded, and then often fixed to or connected at a fixed point, so that movement can take place around the fixed point. So here, when the object is displaced in one direction, it will oscillate up and down, okay, indicating what we are calling as oscillatory motion. Okay, and then here we are saying that for SHM, the acceleration is always directly proportional to the displacement. if I displace it by stretching and leave it, yes, the displacement in this direction, downwards direction, if I leave it, the object will always accelerate opposite to the direction of displacement. Okay, so you displace this way and you leave it, it will accelerate the opposite direction. If you displace it by compression and you leave it, it will, here the displacement is upwards. When you leave it, it will accelerate first in the downward direction, up and down around a fixed point O. So this is what we call as the loaded or the helical spring, okay, which denotes oscillatory motion and also simple harmonic motion. So we are going to look at the qualities of this which makes it simple harmonic by nature. All right. Okay, so at the arrangement we have on the board at the moment is when we have a spring, okay, without any load, and then the B is a spring loaded. So the first one is like what I have in my hand. This is the spring without any load, and look at the length. Okay, now when we have the same spring loaded or weighted, this is it. So the arrangement B is as similar to what I have in my hand. This is a weighted or loaded spring, and this one is unloaded spring or unweighted spring. When the spring is loaded, there is an extension E. Okay, so this is the new length of the spring. New length of the spring. This is the original when there is no weight or load attached or connected to the spring. Okay. All right. Now, when the spring is loaded, there is an extension. Once there is an extension, okay, when the spring is loaded and then it is left, what happens is that when weight or force is attached to the spring, the spring always has the tendency, okay, to restore the spring or the system back to its original form or shape. So there's always what we call a force, a spring force, which is always opposite to the direction of the displacement. So this line O is the point where the spring is at the mean position. Okay, so at the mean position, when we look at it with the original, there is no extension. Now the moment weight mg is attached to the spring, we have the extension, and when the weight extends the spring, springs always has that tendency, okay, to apply a force against the direction of the displacement, okay, to apply a spring force against the direction of the displacement in order to restore the shape of the spring to its original, shape. So there's always a restoring force acting against the extension, and by Hooke's law, this restoring force or the spring force F is directly proportional to the extension E in the spring. This restoring force upwards, F, okay, Hooke's law is saying that is always directly proportional to the extension E when the load or mass is connected to the spring. Okay. 2. The direction of this restoring force here upwards is always against the direction of displacement downwards. Here the object was stretched by the load, so the extension E in the downward direction, and that force the restoring force is also against the direction of displacement. Okay, so Hooke's law is saying that F is directly proportional to minus E. Okay, now mathematically, when we introduce an equal to sign, we have minus K E, K times E, where K is equal to the spring constant, the spring constant, or the elastic constant. Okay, so this is the Hooke's law equation by Robert Hooke. Okay, Hooke's law says that Hooke's law says that provided the elastic limit of a material is not exceeded, the force acting on the material, is directly proportional to the extension E. So what Robert Hooke is saying, that if you have an elastic material and you attach a load, provided the load is not so much, okay, to destroy the elastic limit or the rigidity level or limit of the material, will have the force applied, okay, or the restoring force on the object always directly proportional to the extension in the material, and that is Hooke's law. So as I indicated or explained to you earlier, Hooke's law is this: F is equal to minus K E, where F is the force or the restoring force. F is the restoring force. K is the spring constant. And E is the extension. This value of K, the spring constant, explains how rigid the spring is. Different springs have different values of K. Okay, the higher the value of K, the higher the rigidity of the spring. The lesser the value of K, the lesser the rigidity of the spring. So this, we have a spring like the slinky, okay, and these ones, because they are of different rigidity level, okay, they have different values of K, the spring constant K as well. So that is Hooke's law. All right, now let's move on to see how we can confirm the point that the loaded spring or the helical spring is an example of SHM. Okay, so that's the next point we have. We realize that when the load is attached, connected to the spring, okay, the spring oscillates. So without the load, this is it. When the load is connected to the spring and is left, the body oscillates up and down, or the mass oscillates up and down due to the extension within. Okay, so we have the restoring force F restoring equal to minus K times the extension E. Okay, so the restoring force is that component of the force which causes the acceleration of the body. Okay, so the extension is in a downward direction. The restoring force acts oppositely to it around the equilibrium point O. So the oscillation of the body or of the mass is caused by the restoring force. Okay, that is the net force acting on the mass. If there is a net force equal to the restoring force, okay, then by Newton's second law of motion, force is equal to mass times acceleration of the body. If the body is oscillating up and down, then it means the body is in motion. Okay, therefore the body is accelerating, and the cause of this acceleration of the body is due to the restoring force. Okay, so if from Newton's second law of motion, force is equal to this, so we can equate that ma is equal to the restoring force F restoring. Okay, therefore we can say that m times A is equal to minus K times E, which is the restoring force. Therefore, when we make A the subject, we have the A, which is the acceleration, equal to minus K times E over the mass. Okay, where A is equal to acceleration of the body, K is equal to the spring constant or the elastic constant. M is equal to the mass of the body, and the spring, and E is equal to the extension. Okay, therefore we can say that the acceleration of the body during the oscillatory motion around the fixed point O is equal to minus K on M times the extension. Here, K is a constant. M is the mass of the spring and the load. So what it implies is that this whole component of the equation is a constant. So A is equal to, let's name this part of it Q. Okay, so we have A is equal to minus Q times E, where, let me clean my board, this part of the board, and use this end. Where Q is equal to K on M. So if Q is equal to K on M, then we can say that E, which is E, is directly proportional to minus E. Okay, and E is the extension or the displacement in the spring. Okay, and E is the direction of the acceleration. Okay, as the extension increases, E also increases, and then the acceleration is always directed to the main point or the rest position. Okay, confirming a key attribute or property of a body doing SHM. Okay, so this is all that we are looking for, that when a body is loaded, okay, its acceleration must be directly proportional to the extension or the displacement, and the direction of the acceleration is always against the direction of the displacement in the spring. Okay, all right, so we've been able to prove that the motion of the loaded spring or the helical spring is simple harmonic by this important relation. All right, now let's look at the period of oscillation. Period of oscillation of the loaded spring. Period of oscillation of the loaded spring. Generally, the acceleration of a body doing simple harmonic motion E, acceleration of a body in SHM is given by E is equal to minus omega squared Y. And we just saw that the acceleration of a body of a loaded spring or the weighted spring is given by E is equal to minus K over M. Okay, and here, because we made the extension or the displacement as Y, instead of extension E, let's have it as Y so that we can equate the two. Alright, in this sense we have minus omega squared Y is equal to minus K on My. So we have minus y giving us omega squared is equal to K over M. Alright, and because omega is equal to 2 pi on T. Okay, here before we look at the period of oscillation, when we make K the subject from this relation, we have m omega squared. This is a very important relation for determining the spring constant. The spring constant. Okay. And what we are simply saying, here is that the spring constant K is equal to the product of the mass of the spring and the body times the square of that constant or uniform angular speed or velocity of the body. Okay, so if you are calculating for K, it is equal to the mass times the square of the angular velocity. Okay, so if omega is equal to 2 pi on t, okay, when we square omega here, omega squared is equal to 2 pi on t all squared, which is equal to 4 pi squared on t squared. Therefore, when we equate this by omega squared here, we have 4 pi squared on t equal to k on t squared is equal to k on m equal to k on m. Let's then make t squared as the subject. Okay, if we flip both ends, both sides of the equation, we have t squared on 4 pi squared equal to m on k. Therefore, t squared is equal to 4 pi squared times m on k. Taking the square root of both sides, so squaring, taking square root of both sides is equal to t squared is equal to 4 pi squared m on k. Therefore, we have t given us the square root of 4 pi is 2 pi, so 2 pi out, 2 pi out, then we have m over k under the square root. This is the period of oscillation. The period of oscillation of the loaded or weighted spring. That's the period of oscillation of the loaded or weighted spring. You see, when we compare this to, okay, what we mean is that if we attach the load to the object and cause it to oscillate, okay, the time for a complete oscillation of this mass, the time for a complete oscillation is given by 2 pi times the square root of the mass over k. Okay, 2 pi times the square root of m over k. Okay, when we compare it to the period of oscillation of the simple pendulum. The period of oscillation of the simple pendulum is equal to T is equal to 2 pi times L on G. Okay, so here we realize that the period of oscillation T is directly proportional to the square root of the length of the spring. Here the period of oscillation of the loaded spring T is equal to 2 pi times M over K. Okay, here too, K is constant. K is a natural property of every different spring. So it also implies that the period of oscillation of a loaded spring is directly proportional to the square root of the mass. The mass connected, which is this, to a spring can vary. As we vary the mass, we can have different values of T. Okay, with the same mass, as we vary, with the same spring, as we vary the masses, we can get different values for the period of oscillation. Okay, because with the same mass, K is constant. But if we keep on changing the masses, we can get different oscillation. Let's try it. Let me try and reduce. When this is it, look at the oscillation. When we have the full load, look at the oscillation. Okay, and let me remove some of the masses. Let's take off some of the masses, and we all see what happens to the mass. Okay, so of taking one, let's take another board. I've reduced it, and when the object, you see, this is moving so faster compared to the earlier situation. Okay, now let me continue removing some masses. This is 100 gram. Let me take the 100 gram mass off, and then pause at this. God, so fast to the point that if I had not been so quick, it would have. Okay, so as we reduce the mass, what happens to it? Okay, so make your conclusion as we vary the masses on and on. So this is how what the period of oscillation of a loaded spring depends. It depends on the square root of the masses, just as the period of oscillation of a simple pendulum. This is a simple pendulum. Depends on the square root of the length. For the loaded spring, which is this is the loaded spring. The period of oscillation depends on the square root of the mass. Okay, that's the difference. All right. Another important point we can look at is when the load is attached to the object, there is the weight causes an extension E, and that is indicated by, so here when the load is suspended on the spring, by virtue of the weight of the object, there is an extension E. Now at C, we still cause a stretch by causing a downward displacement, a stretching of the spring. And so by applying a force to cause or to stretch the spring, we have an additional extension by virtue of the stretch Y. Okay, so this is A. A is this when there's no load. B, when we attach a load, by virtue of the weight of the object, there is an extension E. Now C, the object is then displaced by stretching it. Okay, and when that is done, when the object, the spring is stretched and then is left, there is that sporadic oscillation at a higher amplitude. Okay, meaning there is a restoring force acting against the direction of the extension by the weight and then the stretch by application of the force, which gives us an extension Y. So the restoring force which will act against the direction of the extension E by the weight and then the extension by the application by the stretch Y would be equal to F restoring would be equal to minus K times the displacement. By here, the displacement or the extension within is equal to E plus Y. So this will be the magnitude of the restoring force which will act against the direction of the downward direction of E and Y. Okay, so because when that is done, okay, the body continues to oscillate. In the first situation, by the weight of the object, the body oscillates and then we keep it in equilibrium. So at equilibrium here, at B, because the body is in equilibrium, meaning the net force acting on it in the along the vertical plane is 0. So we have the weight mg, which is equal to the restoring force acting oppositely to the direction of extension, F restoring, giving us minus F E. Okay, but when we consider the absolute value of this, we have mg giving us Fe, because we are interested in the magnitude of the weight and then the restoring force, even though we know the restoring force is acting against gravity. Okay, all right. Now when we come to C, because as we stretch the spring and leave, it will continue to oscillate vertically. Okay, there is a net force on it causing the consistent or constant vertical oscillation of the body. So that net force, the net force responsible for the vertical acceleration of the body is equal to, so net force will be equal to the downward weight of the object mg minus minus the restoring force. The restoring force in the opposite direction. So F restoring. So we have the net force acting on the body equal to mg minus k e plus y. Okay, mg minus ke minus ky. When we multiply through by the minus. Now because mg is equal to sorry, this should be k, not f. Is equal to ke by magnitude. We can, in place of ke, we can substitute this for us to have the net force equal to mg minus mg minus ky. Okay, mg cancels out, and so we have the net force giving us minus ky. Alright, a net force is always responsible for causing acceleration in a system. So if we are looking for the vertical acceleration of the body due to the net force, okay, the vertical acceleration of the body due to the net force acting on the object vertically, we have the net force equal to Newton's second law, mass times acceleration, which is equal to minus ky. Therefore, E is equal to minus ky on n. Okay, giving us the same relation we derived earlier for the acceleration of a body, as the acceleration of a helical spring or the loaded spring. So no matter what I'm trying to say is that no matter how you look at it, by considering a natural extension of the spring by the weight attached to it, or by displacing the weight, okay, by an extent y and leaving it to oscillate, it will still give you the same relation for the acceleration of the helical spring, where K on M is a constant. K is a spring constant. M is the mass of the load, and then the spring attached. Okay, so these are the key information you have to know about the helical spring or the loaded spring. One, we realize that K, the acceleration E, is equal to minus K over M. Okay, the acceleration is equal to minus K over M. Alright, and then we also got the relation for the period of oscillation, where we realize that the equation for the general acceleration of a body is equal to I squared omega squared y, and for SHM is equal to minus K over my. Therefore, omega squared is equal to Km, and from this we got a relation for spring constant omega squared. Then we determined the period of oscillation, okay, because omega is equal to 2 pi upon T, it implies that T from this equation, alright, is equal to 2 pi times the square root of n on k. This is a relation for the period of oscillation of a helical spring. So the equations we derived so far are 1, 2, and then 3 for the helical or the loaded spring. Okay, so these are the key concepts in the motion of the helical spring as it pertains to simple harmonic motion. Thank you so much for making time with me. I'll see you once more next time in next concepts under simple harmonic motion. So in our next meeting we'll look at the energy possessed by a body in simple harmonic motion, okay, as the energies, potential energy and kinetic energy along the motion interchanges. Okay, so we'll look at expression for potential energy, the expression for kinetic energy, and then the total energy within, and then how we can graph this individual energies and then the total energy as well. Alright, so stay tuned to the next edition. Thank you so much, and